Welcome to this next video in the playlist on group theory. In this video what we're going to talk about is the product of two subgroups. Okay, so we'll begin with the definition of the product of two subgroups. So what we're going to have then is some group, capital G, which we'll be working with, and this is just a general group, so it doesn't need to be anything fancy. It doesn't need to be an abelian group, it doesn't need to be a finite group, it can be an infinite group. It's just an arbitrary group, capital G. Okay, now to define the product of two subgroups we're going to need two subgroups to actually product together. Okay, so we will have now two subgroups which we will throughout the video be calling H and K, capital H and capital K, which are both going to be subgroups of the group capital G. And again, these are just general subgroups, so they don't need to be anything fancy, they don't even need to be finite. They can be infinite if you wish, although some of the theorems will require them to be finite, but I will state that at the start of that theorem. Okay, so H and K then are our subgroups of the group capital G, and now what we're going to do is define the product of these two subgroups. Okay, and this product is just going to be written H next to K, like so. So this is the product of the two subgroups H and K. Now before I even define it, what I want to point out is that we are not doing the direct product. So previously in this playlist on group theory, I have had a video entitled The Product of Two Groups. Now the proper name for what we define in that video is the direct product of two groups. Okay, so although I called the video The Product of Two Groups, what we actually do in that video is properly called the direct product of two groups. In this video we are not going to be taking the direct product of these two subgroups. The direct product would be written H and then you put a cross in between it and K. So this would be the direct product of the two subgroups H and K. And that's perfectly doable. You can construct that because H and K, after all, are groups in their own right, so you can indeed take the product of them. However, it has absolutely nothing to do with them being subgroups of this larger group, capital G. Okay, this would have been definable if they were just two completely unrelated groups, whereas H and K are not unrelated. They are both subgroups of this larger group, capital G. What we're going to define in this video, HK here, the product of two subgroups, requires the two things that we are producting together to be subgroups, whereas the direct product doesn't require them to be subgroups of some larger group that you're working in. They can just be two arbitrary, completely unrelated groups with completely different symbols. Remember, the way that we construct this thing is just we form all pairs of elements from the two groups. So we form these ordered pairs of an element from H with an element from K and define the composition on those elements. Those elements are going to be the elements of this new group, the direct product of H and K, and we define composition component-wise using the composition laws from the two groups that we are direct producting together. But you don't require the two things that you're producting together in that case to be subgroups. They can be arbitrary, completely unrelated groups. Okay, so we are not talking about the direct product here, and I want to stress the difference right at the beginning. Okay, so we are not doing this. We are looking at a different type of product which does require the two things that we're producting together to be subgroups. Okay, so that we've got some larger group in which we are working. Right, so how are we going to define the product of H and K? Well, initially the product of H and K then is just going to be a subset of the group capital G, and in all cases it's not actually going to be a subgroup. In the most general case it's just going to be a subset of the group capital G that you can build. Okay, we will obviously be very interested in the cases where it actually does end up being a subgroup, but it doesn't have to. Okay, and it's defined just to be the subset of the group that contains all elements that you can obtain by taking some element of capital H, which I'll call little h, and composing it with the group composition law of the larger group. That's why we need to have this larger group. If they were completely unrelated groups, we wouldn't be able to do this. Okay, composing it with some element little k, which is an element of capital K. So little h is an element of capital H, and little k is an element of capital K, and I'm sorry that looks like a big K, but it's supposed to be a little k. Okay, I'll just colour code it to make it more obvious. So this is a little k that's an element of larger K. Okay, it's much easier with little h to distinguish it from larger h. Okay, so to construct this subset of the group then, what you do is you take every element from capital H, and one by one you compose it with every element from capital K. You go through every possible combination you can dream up. Okay, so you do it systematically, you tick them off one by one, go through every single combination of an element of H composed with an element of K, work out all the answers, and all the answers are going to be elements of G, okay, because of course we're just composing two elements of G together. That's why we require both of these subgroups to be in some larger group. Okay, remember, when you're doing the direct product, you don't need that at all. Okay, but with this, you certainly do need them to both be in some larger groups so that you can actually compose the elements of the two subgroups together. Okay, you work out every single one of these, and you stick all of the answers into this great big set, and what you will end up with is a subset of the group capital G. Okay, so I hope we can agree that this is going to be a subset of the group capital G, because of course you're just composing elements of capital G together. Whenever you do that, you're always going to get an element of capital G because groups are closed under composition. Okay, so you're certainly going to get a subset of the group capital G. Okay, so there's the definition. That is what we're going to define the product of two subgroups to be equal to. And as I say, at the moment, it's not necessarily going to be a subgroup itself, although we will be extremely interested in what conditions need to hold true in order for this to actually be a subgroup. Okay, right, and we will explore that in this video. So the first thing we're going to do is we're going to discuss something which I'll just call Theorem One. So in fact, I'll spell out what we're going to do for the rest of this video. We're going to study this, okay? We're going to study three incredible theorems about this. Theorem 1, Theorem 2, and Theorem 3. Okay, those aren't the names that are generally given for them, they're just names that I'm using because I'm boring. Okay, and Theorem 2 and Theorem 3 are going to be about conditions for when this is a subgroup. Theorem 1 is going to be about what you can say about the order of this if the two subgroups that you're producting together have finite order. And we're going to begin with Theorem 1. Okay, so I will put the title, Theorem 1 here. Right, so let me state Theorem 1 now. As I say, for Theorem 1 to work, we need the order of the two subgroups that we are producting together to be finite. Okay, so I'll put that as my first initial condition. So the order of H and the order of K are going to need to be finite now. Okay, so they're going to have to be strictly less than infinity. So that's just a shorthand way of writing that they need to be some finite natural number. Okay, so here's Theorem 1 then. Theorem 1 says that if this is the case, then you can conclude that the order of the product of H and K is equal to the order of H times the order of K, which are both finite natural numbers, divided by the order of H intersection K. Okay, so that's what we want to now try and prove as Theorem 1. And you might look at this formula and think, oh goodness, what a boring formula, why should I care? Now, Theorem 1, although the formula, it has its moments, it's useful occasionally, it's not the main goal of Theorem 1. The main goal of Theorem 1 is not to prove this. The main thing that I want you to take from Theorem 1 is the proof strategy, okay? The main goal of this is not to actually arrive at this formula. As I say, the formula is occasionally useful, but the important thing isn't the formula. The important thing is the reason the formula is true, the understanding that you will get through the proof of this theorem. Okay, that's far more important than that actual formula. Okay, so if you are looking at this formula thinking, oh goodness, I don't care, don't worry. The proof will give you a lot greater understanding of the product of H and K than this formula actually gives you. The formula is just a means by which we can explore the product of H and K to gain some interesting insight about it. Okay, so The proof is going to give you a lot of interesting insight into the product of h and k, if indeed the order of h and the order of k are finite. Okay, so let's begin the actual proof then. Okay, so the proof of Theorem One then. So, proof. So, in order to prove this, what I want you to firstly appreciate is another interpretation, or a very useful interpretation, of what the product of these two subgroups h and k is actually equal to. Okay, so remember h and k, the product of h and k here. Okay, what we have to do to construct this is we have to take everything in h and compose it with everything in k. Now what you could actually do to construct this subset then is you could actually just union together loads of left cosets of the subgroup k. Okay, you could take all left cosets of this form, h multiplied by k, so the left coset of k under this element h, where little h is an element of capital H. And I claim that if you unioned all of those together, you would actually end up with the product of h and k. Okay, now let's just think a little bit about why this is going to be the case. So, the product of h and k is just all things of the form an element of capital H composed with an element of capital K. If we go through all the elements of capital H here and take the left coset of K under that element, we will be producting each of these elements of H with every single element of capital K, and then we'll be getting loads of these cosets of capital K and unioning them all together. And of course what we will overall end up with is the set containing all elements of the form an element of capital H composed with an element of capital K. So truly, this is a way that you could construct the product of h and k, and it's a useful first way. This is the first useful insight that we're now getting into the product of these two subgroups h and k, that in fact what you're just going to have to do here is union together lots of cosets of k, all cosets of k in fact, that contain an element of h. Okay, so to draw this picture then, to draw a picture to summarise this, let's have our entire group, capital G, represented by this box. So I'll just colour this in a certain colour. So we'll have the group coloured in red here, so this is the entire group. Okay, now let's draw on K. So I'll put K down here. Now of course we know that K will partition the entire group up into left cosets, so I'll draw that on here. Now for the purpose of the picture, obviously I will draw it as though the index of K and G is finite, although we haven't made that as an assumption for Theorem 1 to be true. Okay, but clearly I can't draw an infinite number of cosets for K in G. Okay, but so I'll just draw a finite number. So we'll chop it in half firstly, and I'll try and partition it up into 8 cosets here. Okay, so that's 5, 6, 7 and 8. Okay, so I've got the index of K in G, as far as this picture is concerned, is 8, but more generally it could be infinite if indeed the order of the entire group is infinite. Okay, right, so there is K partitioning the group capital G up into cosets of K, left cosets of K, and now what I want to draw on here is H, so let's just draw on H here. And you'll notice how I'm making H coincide with the line of this coset here, and you'll understand that in a moment. Okay, you will understand that. So here comes H in pink here. Okay, so this is capital H here. And now, to actually construct then the product of H and K, what we need to do is go through all of the left cosets of K that contain elements of H. So we'll start with this portion here. Okay, so of course this is the intersection of these two subgroups, which I'll call H intersection K. So this is all looking hopeful because there's H intersection K in the formula. So we're starting to see things that are appearing in the formula. So this is all starting to maybe make sense. Okay, so of course we know that that will be a subgroup of capital G, because whenever you insect two subgroups together you get another subgroup. Okay, so what we would do is we'd start off with this, and whatever element you took in H intersection K, and you know there might be lots of elements in H intersection K, they would all generate the same coset of K. They generate K itself. Okay, so they'd all generate this coset. Then we've got another little portion here, another portion of H that's in a coset here. All of the elements of H that are in that coset would generate this coset, etc. for all of these ones. So in fact, what the product of h and k is going to equal, I hope you can appreciate on this picture, is this box here. Okay, and in fact that's a really important understanding of what the product of h and k really means. Okay, it really is the extension of these cosets of h that you can partition h up into by taking the cosets of k to the entire group. Okay, so what you're really doing is you can partition the entire group into these cosets of k, and you're now looking for all of those cosets that have elements of h in them, and you're taking all of those cosets, and that's really what the product of h and k is equal to. Okay, later on we'll be able to give another bit of insight into this. I'll give another line for what the product of h and k is equal to. I sort of kind of gave it in the in what I've just said, but we'll come back to that. At the moment, I'll say it again. Your interpretation of the product of h and k is this, that you can partition the entire group up into the cosets of k. You're now looking at those cosets of k that contain elements of h, union all of those together, and that will equal the product of h and k. That's our current understanding of what the product of h and k is equal to from this picture. Okay, so now what we can do is, aiming towards this formula, we can say that the order of the product of h and k is going to be the size of each of these cosets, and of course the size of each of these cosets is just going to be the order of k. Okay, all of the cosets of k are going to have the same size as k, and now all you need to know is how many of these cosets do you actually have that have elements of h in them. And you might say, well, that's easy, it's just going to be the number of elements in h that you have. But no, don't be so hasty, because it's not necessarily true that every single element of h is in a separate coset. You might have loads of elements of h that are all in the same coset. Okay, so they'd be generating the same coset of k, and in this union process here, you'd be unioning on a left coset of k that you've already put in, so you wouldn't actually be adding in any new elements at all. So you don't want to just product by h. Instead, you need to somehow conclude that what we need to do is times by the order of h divided by the order of h intersection k, but we'll understand why in just a moment. Okay, so we need to times by what I'll at the moment just call n, where n is the number of left cosets of k that contain at least one element of h. Okay, so how are we going to access this number? How many cosets then of k do contain an element of h? Well, here's my claim, and I hope this should be intuitive to you from the picture, but of course it will require a proof. Okay, the claim is this, that what you can actually do is pull out your subgroup h here. Okay, so pull out this subgroup h here. Okay, so I'll colour it in purple here, like so. And then, of course, one of the subgroups of this is going to be h intersection k down here. And I'll colour that in orange. So here is h intersection k here, which was here previously. So I've just pulled h out. I've imagined, if you like, chopping away all of the rest of the group that's outside of h, the complement of h, and then just viewing h as a group in its own right, which is perfectly valid to do that. And now what I can do, of course, is I can partition h up into the left cosets of h intersection k. Okay, and I claim that the number of these cosets that I will get is the same as the number of cosets that I've got over here of k that contain elements of h. In fact, these little portions here will be exactly the same as these portions here, which I hope is obvious from the picture, but of course does require proof. Okay, so this one will correspond to this one here. This one will correspond to this one here. This is just a picture, I will prove this in a moment. Okay, this one corresponding to this one here, this one, and it's making a mess, so I'll stop. Oh, actually, there's only one more, so I might as well just do it. But this one will correspond to this one here. Okay, and of course, these intersections of these cosets of k that contain elements of h with h, you have the same number of those as you have of cosets of k that contain h. So in fact, my claim is that all we need to do is count how many cosets are we going to get in the subgroup capital H when we partition it into the left cosets of H intersection K. But that's an extremely easy answer, okay, because each of these cosets is going to contain how many elements? Well, it will contain the number of elements in H intersection K. So all you need to know, all you need to do in fact, to work out how many cosets you'll get is just divide the entire order of the group by the order of a coset, which is the order of H intersection K, and that will give you how many cosets it must partition the entire subgroup up into. So my claim then is that this is going to equal Rn. Okay, so this is going to equal n. Substitute that in there and of course you get the formula. Okay, so the final thing then that we need to prove is that actually yes, if we partition up H into these cosets of H intersection K, then these cosets correspond to a coset over here of K that contains an element of H, and in fact these cosets here are just the intersection of the coset of K with the subgroup H. So what I'm going to do then is create a function which I'll call phi, which is going to take a coset here and map it onto a coset over here, a coset of K that contains an element of H. And the way this mapping is going to work is it's going to take an arbitrary coset over here. Now what would I call? I'll need some notation here, so I need some notation for my cosets. So of course, let's say this this coset here contains an element little a, which is an element of capital H. So little a is an element of capital H. We'll call this coset a bar, and because it's the coset of H, a coset of H intersection K, I'll colour that bar in orange, and the colour coding will become important in just a moment. Okay, so here's a coset. This is a coset of H intersection K, which contains the element A. So I hope you understand what I mean by that notation. And I'm going to now map this onto a coset over here, which is going to be a coset of K. And of course, what coset am I going to map it onto? Well, it'll just be the coset that contains A. So here is A again. And now it will be the coset that contains A, but this time it's going to be a coset of K. It's going to be this entire coset here. So I'll map it onto the coset that contains A, but this time it's a coset of K, and I'll colour that bar in green. So this is the way I'm going to define this mapping. It's going to take a coset here, and the way it's going to decide which coset over here that it's going to map it onto, and here the codomain here is just those cosets of K which contain elements of H. I don't care about the cosets of K that don't contain elements of H up here. I just care about those cosets of K that do contain elements of H. Okay, so the way this mapping is going to work is it's going to take a coset here, it will say find me a representative of this coset. I will look and find which coset of K over here contains that representative, and of course that will be a coset of K that contains an element of H because the representative is an element of H, and the answer then will be the coset that contains that representative. So what I now need to prove to you is that firstly this is a well-defined map, and secondly that it's a bijective map, because if I can prove it's bijective, I have proven a bijective correspondence between the cosets here of the subgroup H under this even smaller subgroup H intersection K and the cosets of K that contain elements of H, and therefore I am justified in saying that the number of these is equal to the number of these, and therefore the formula is true. Okay, so firstly then, let's prove that this mapping is well defined. So what do I mean by well defined? Well, I talked about using a representative A, so I need to make sure that it doesn't depend on which representative you use. Okay, so if you picked some other representative in here, okay, so some other representative in the same coset as A, of course that will be of the form A composed with, what should I call it? I'll call it N, where N is some element of H intersection K. So this is an element of H intersection K. Okay, that will be my other element in here, and I could use that as a representative as well. And I want to make sure that this will now still be in the same coset of A over here. Now, of course, that's going to be true, because all of the elements that are in the same coset of A, where we're taking cosets of K now, will be of the form A composed with K, where little k is an element of capital K, and anything that's in H intersection K will certainly be in K. Therefore, this is still going to be in the coset of K under A, if it was in the coset of H intersection K under A. Okay, so that shows that it is well defined, and if you haven't understood that argument, all I'm trying to say is that no matter what representative you pick in this coset here, it will always be in the same coset, and therefore the answer in terms of the coset over here will always be the same. Okay, and the reason that is because if you're in the same coset here, you're certainly going to be in the same coset over there, because H intersection K is just a small portion of K. So indeed, when you take the coset of A over here, you're going to compose it with all the elements of K, so you're certainly going to compose it with all the elements of H intersection K, so you'll get the full, the full host of elements in the coset over here. Okay, so it is well defined. Now what we want to show is that it's bijective, and to do that we need to show that it's injective and surjective. Now surjective is incredibly easy, injective is a little bit more difficult, so we'll start off with injective. So what I want to show is that you cannot have two different cosets here being mapped onto the same coset over here. So how am I going to do that? I'm going to do it by contradiction. I'm going to suppose that we have two cosets over here that are being mapped onto the same thing. So let me do it here. So let's say we've got this other coset here, and we'll call this other coset B bar. So let's say that this coset contains an element B here, and I'm sorry this is so small. Okay, so I've just taken the coset below, stuck in the element which we're calling B here, and then named the coset after that representative B bar. Okay, so now what we're supposing is that phi of A bar is equal to phi of B bar, i.e. both of these cosets are going to be mapped onto the same thing. And of course these are the cosets of H intersection K, so I'll colour them in orange. So of course what does this mean? Well, phi of A bar, just by definition, will equal the coset of K that contains A, and phi of B bar will just equal the coset of K that contains B. So I'm now saying that the coset of K that contains A is equal to the coset of K that contains B. Okay, so these two things are in the same coset, so that would mean A was in the same coset as B, which would imply that A was equal to B times some element little k, which is an element of capital K. Okay, that's all it means for them to be in the same coset. Now, why is that not possible? Well, remember A and B here, these were both elements of capital H. Okay, they were both representatives in these cosets of H intersection K in H. So they're both in H. So what I could do is just rearrange this to B inverse A is equal to K, but B inverse A must be an element of capital H, because this is a subgroup, and therefore it's closed under composition and inverses. So that now implies that this K here, little k here, is actually an element of H. Okay, so that would mean that little k was an element of both H and K, so it was an element of H intersection K. So now go back to this formula. That would imply that A and B were in the same coset of H intersection K, because now A is equal to B times an element of H intersection K, so it would mean that A bar and B bar as cosets of H intersection K were actually the same thing, and that's a contradiction because I assumed that they were initially different cosets. So indeed, two different cosets here cannot be mapped onto the same coset over here. They will be mapped onto different cosets, so indeed it is injective. Okay, and finally, surjective, so I want to prove that it's onto. I want to prove that every coset of K over here that contains an element of capital H, and that is important. I'm not saying that every coset of K in the entire group will have something over here corresponding to it. Just the cosets of K that contain an element of capital H will have something over here being mapped onto it. Okay, so I want to prove then that every coset of K over here that contains an element of capital H has something over here being mapped onto it. Why is that going to be the case? Well, any coset over here of K that contains an element of capital H will indeed contain an element of capital H. Okay, that element of capital H will be in one of the cosets here, and that coset will then be mapped onto that by this mapping, because just look at the way the mapping is defined. It takes any coset onto what a representative of that coset is mapped onto, and you don't need to worry about it being well defined because we've already checked that it is well defined. So indeed this is a beautiful bijective map. There is a bijective correspondence between these cosets of H intersection K, okay, where they're partitioning up the subgroup capital H, and these cosets of k that contain elements of capital H. So here, if you like, is the new interpretation of the product of H and K. So when you've got these two subgroups, H and K here, what you can do is you can intersect them and construct H intersection K here. Then you can partition up your subgroup capital H into the left cosets of H intersection K. And now what you can imagine doing to create the product of H and K is you want to extend those cosets now out into what they will be as cosets of K in the entire group capital G. So you're almost extending these cosets in this way so that they now include all of these new elements here, and that's how you're creating this product of H and K. Okay, so that's the insight that I hope that you have gained from Theorem 1, the insight of what truly this product of H and K actually is, rather than just the appreciation that this formula is true. Of course, I hope you've I hope you've got that as well, but more important is the understanding that you've now gained about what the product of H and K can be interpreted to be if indeed the order of H and the order of K are finite. Okay, so we'll have a break there, and in the next video we'll go on to Theorem 2, which concerns when this product of H and K is actually going to be a subgroup.